Good morning, everyone. Are you all logged in? Are there any questions from what I have discussed so far? Hi, good morning, Glenna. So, are there any questions? So, I'll wait for a few minutes. Good morning. Okay, so now let me share the full screen. All right, so we can begin today's lectures. Right, so what we have seen so far is that stars are formed out of cold gaseous clouds, which, when it cools further, they start contracting because the pressure support is not sufficient. And when they start shrinking, the gas gets compressed. And we all know from our laws like Boyle's law, Charles' law, etc., that when a gaseous system gets compressed, then it also gets heated up. So when a gas cloud starts shrinking, then the core temperature of this gas cloud starts increasing. And when the temperature goes to about 10 million degree Kelvin, then the protons in the core, they start undergoing thermonuclear fusion, in which effectively four protons turn into one helium nucleus. And the mass deficit, I had asked you to calculate the difference between four proton rest mass and the helium nucleus mass. And this mass deficit is what powers the star, in the sense that the core of the star becomes hotter, and therefore the pressure also becomes larger. And this core pressure being higher, and there is a pressure gradient, so that the pressure decreases outwards. And it is the pressure gradient which helps the star maintain a quasi hydrostatic equilibrium. All right. And then, furthermore, we saw that because the surface of a star emits like a black body, and we already know that by studying the full spectrum of the black body radiation. What is the black body radiation? Black body radiation is nothing but collection of electromagnetic radiation or equivalently photons which are in thermodynamic equilibrium with surrounding matter. So, what one is saying is that the radiation that is emanating from the surface of a star, this radiation just beneath the surface is in thermal equilibrium with the hot gaseous matter that makes up the star. And by studying the intensity of the black body radiation emanating from the photosphere over a range of wavelength, one can find out the temperature of the black body radiation. That means the temperature at which the radiation and the matter, the surface matter of the star, is in thermal equilibrium. That temperature can be found out by estimating the intensity of the radiation over a long range of wavelength. And in particular, we know that by using the Jeans law, which says the intensity, maximum intensity, the wavelength at which black body radiation attains the maximum intensity, that wavelength multiplied by temperature is a constant, and therefore this peak intensity and the wavelength at which the black body radiation attains the peak, that using the Jeans law one can find out what is the temperature of the black body spectrum. And we also know from the Stefan-Boltzmann law the integrated intensity, integrated over all wavelength, the integrated intensity over the wavelengths is a function purely of the temperature for the black body spectrum, and it goes as sigma multiplied by fourth power of the temperature, where sigma is the Stefan-Boltzmann constant. And using that, because this is the intensity of the black body spectrum, and therefore, since the surface area of the photosphere is 4 pi times the radius of the star, we can find out what is the luminosity of the star. Luminosity will be simply sigma multiplied by t raised to the power 4 times 4 pi square of the radius of the star. So luminosity can be estimated as a function of radius, but the luminosity also can be ascertained by measuring the flux and knowing the distance of the star. Combining both of them, one can estimate the radius of the star. And this is what astronomers keep doing. I have already talked about the apparent magnitude, the absolute magnitude, how the apparent magnitude differences are related to the logarithm base 10 of the ratio of the flux from a star. And I also discussed about the correlation which late astronomer Henriette Swart-Leavitt had established for Cepheid variables, because of which one can estimate the luminosity independently. So if the luminosity is known independently, flux is measured, one can find out the distance also. So Cepheid variables, by virtue of the work done by the astronomer Henriette Swan-Leavitt, gave a big boost to estimation of faraway objects in our universe. In particular, it established that the faint nebulae like Andromeda and others were actually galaxies by their own right, but lying at very large distances. Right. And we also saw that various stars have different magnitudes, like sun is very bright, so therefore the apparent magnitude is more negative than minus 25, while naked eye, the faintest star that one can see with our naked eyes is slightly over plus 5. Okay? And I also told you what is the definition of the maximum magnitude. Here, I had pointed out one typographical error. Please correct it. This is not 10 parsec, but it should be 1 parsec. Okay. And I said that absolute magnitude is nothing but the apparent magnitude that a luminous object would have if it is brought to a distance of 10 parsec. Okay. So when you put d equal to 10 parsec, you find that the apparent magnitude minus absolute magnitude goes to 0. And in particular, I told you that how, although Sirius appears very bright, so that the apparent magnitude is much less than the star HD 49980, its magnitude, apparent magnitude, is much larger because its flux, received flux compared to the received flux from Sirius is smaller, but in reality, it is the luminosity is higher. And in fact, here is a slide which gives the luminosities of some of the prominent stars. All right. So let me go slow because this slide is being shown for the first time to you all. Right. So the nearest star to our Earth is Sun. Sun's luminosity is close to 4 times 10 raised to the power 33 erg per second. Okay. And this is termed as the solar luminosity. So L sun, or L with a subscript circle with a dot. Circle with a dot is a symbol for sun, and the solar luminosity is close to 4 times 10 raised to the power 33 erg per second. And we have already encountered that mass of sun is 2 times 10 raised to the power 33 grams, which is the solar mass. And the solar radius is, that means the radius of the photosphere is 6.96 times 10 raised to the power 10 centimeter. Now let's go to some of the other bright stars. Canopus. Canopus, or the star Agastya, which from Delhi can be only seen very close to the horizon. But if you want to get a good view of Canopus, you have to go southwards from Delhi. In fact, from Chennai, the Canopus star is visible very prominently. And Canopus, or Agastya, it is 10,000 times brighter than sun. Brighter meaning its luminosity. The amount of energy Agastya is radiating per unit time is 10,000 times our sun. It is also heavier by a factor of 8 as far as mass is concerned. So it is 8 times heavier than sun. It is also very large. The radius of Canopus is about 71 times radius of the sun. And it is this factor, remember, R square enters in the luminosity formula, and therefore mass being large and radius being 71 times sun's radius makes the Canopus luminosity so high. Another star, Vega, it is 40 times more luminous than Sun, and its mass is about 2.1 times solar mass, and radius is 2.4 times solar radius. While the Sirius A, remember the constellation Sirius, which is uh, very close to the right leg of the Orion constellation, and the brightest star in the Sirius constellation is called Sirius A, and Sirius A, it's 25.4 times more luminous than Sun. Again, its mass, it is twice heavier than Sun, while the radius is 1.4 times the solar radius. And historically, Sirius A is also, there is a companion to Sirius A called Sirius B, which is extremely faint. And when it was discovered by astronomers, the size was estimated, and using the same method that I talked about earlier, and it turned out that the size is close to 6,000 kilometer, and that's how the white dwarf stars were discovered. All right, now suppose you do the following exercise. You look at all the stars that you see in our galaxy and find out the spectrum of each of the star. If you have a powerful telescope and it has a good spectroscopy measurement device in it, then you can measure the spectrum of all these stars, and you can also find out the either the absolute magnitude, or which is equivalent to measuring the luminosity. This can be done only if one knows the distances of the stars, but what one measures is the flux, or equivalently the apparent magnitude. But to get the absolute magnitude or the luminosity, one has to know the distance of the star, and that distance for majority of the stars which are within few hundred parsec, one can use the parallax method to measure the distances. Otherwise, one needs to use other measurement techniques to estimate the distance of the stars. And if you plot the absolute magnitude as a function of the spectrum, let's say you're plotting the apparent magnitude at a given frequency. So let me show the plot. Yeah. So the color, for example, one way to find out the temperature of a star is to find out the apparent magnitude at some filter called blue filter, and similarly apparent magnitude at B filter. So the difference in the magnitude will cancel out the distance effect, and what you will get is effectively a marker of the temperature of the star. And what you see in the y-axis is the luminosity of the star in units of sun. For example, if I take the point 10, what this all the stars along this horizontal line in this plot have luminosity which is 10 times the solar luminosity, while all the stars here in this horizontal line are 1,000 times more luminous than the sun. And now, if you make observation of many stars, and as you can see, you see a pattern. You see a band, a snaky band of stars, okay? All the stars which are lying in the snaky band are the main sequence stars. That means stars in whose core four protons are effectively fusing to make one helium nucleus. And as you can see, that the more luminous stars, they tend to have a higher temperature. That means they are bluer. Remember, this is magnitude at blue filter minus magnitude at the visible filter. Therefore, more luminous stars, main sequence stars, they appear to be bluer compared to stars, main sequence stars, whose luminosity is not very high. Here, you see a band of stars which are very luminous, no doubt, but they are redder. See these stars? These can be more than 100 times luminous than the star, but their magnitude at the blue filter, that is high frequency filter, okay, is larger compared to V filter. Magnitude larger meaning the flux density is lower. So therefore, these stars are luminous, but their temperature is lower. When can that happen? Remember the expression that I had derived. The luminosity is 4 pi r squared times sigma t raised to power 4. So T is small, but luminosity large, meaning R is very large. So these are the giants, so-called red giant stars. But there can be other stars which are the supergiants, okay, which are very massive stars. They go on to become supergiants when the core becomes depleted, hydrogen depleted, while the envelope immediately surrounding the core, their hydrogen burning takes place, so that they expand very to large radii. On the other hand, white dwarfs, you can see how faint the white dwarfs are. Why are they fainter? Although they can be very blue, they can be very hot, but they are very faint. Their the reason why the luminosity is very low, although the temperature can be very high, is the size itself is very small. This plot is named after the astronomers Hertzsprung and Russell, who for the first time analyzed and found the pattern in the distribution of in the stars in the luminosity versus temperature diagram. The next plot is a cartoon. This is not actual data, but essentially showing the basic plot that I just described. So again, the y-axis is absolute magnitude, which is related to the luminosity of the star. And now the x-axis, instead of apparent magnitude at B filter minus apparent magnitude at V filter, the x-axis is directly plotting the temperature of the star. As you can see, that the temperature is increasing as you go leftwards. So that has to be noted. So this Hertzsprung-Russell diagram, the x plot the temperature is actually increasing as you go leftwards. So this has to be noted. And we see more luminous stars have higher temperature in the main sequence. All the stars that are in the main sequence, they have more luminous stars tend to have higher temperature. And similarly, the giants, okay, the red giants like Aldebaran, etc., they are having high luminosity, but the temperature is lower because they have expanded. So R is more, luminosity is large, although the temperature T raised to power 4 factor is smaller. Now, here is another star which is of great interest these days called Betelgeuse. Betelgeuse is a star in the Orion constellation, and currently the astronomers, they are keenly observing the Betelgeuse, which is a supergiant, because currently Betelgeuse star is showing a lot of variability. Its flux is changing over time, and astronomers, uh, they think that Betelgeuse is about, the core of Betelgeuse is about to collapse into a supernova. So the coming days are going to be very exciting as far as the Betelgeuse star is concerned, because we may soon observe a supernova, that means an exploding star, at our very backyard. The last nearby supernova that was observed by astronomers is the supernova 1987A. So, by the very classification, you already know that this supernova was observed in the year 1987, and the supernova uh, was not part of our Milky Way galaxy, but it was part of the large Magellanic Cloud. While Betelgeuse, it is in our galaxy, and if the Betelgeuse turns into a supernova, very soon we will see a supernova within our um, span of our lifetime. So everyone is excitedly looking at the Betelgeuse star. Right. Now, uh, again, this is something I have already flashed, and I have uh, tried to explain to you that different mass stars evolve in a different way. So sun-like star will eventually become a red giant, and finally the core, which will be carbon, nitrogen, oxygen rich, will become white dwarf, while very high mass stars, they, depending upon the core mass, will either become a neutron star or will become a black hole if the core mass is less than or about 2.5 to 3 solar mass. Then the core, after the envelope explodes as supernovae, the core collapses into a neutron star. While if the core mass is greater than 3 solar mass, after the supernova explosion, the core will collapse to form a black hole. While the low mass stars, the core will just die as a brown dwarf. Okay. Right. But let me go back to one of the curious things that I had shown to you early on. Last class, I had shown the slide in which I described that the following thought experiment concerning astronomical object. Remember, it's a pure thought experiment. So consider sun. We know the photosphere of our sun has a temperature of about 6,000 degree Kelvin. And let's consider a red giant star. Let's say the surface of the red giant star's temperature is about 3000 degree Kelvin. So 6000 degree Kelvin here and 3000 degree Kelvin over the red giant. And in the thought experiment, what I do is I connect the photosphere of sun to the outer surface of the red giant star. And the laws of thermodynamics tell me that heat will flow from higher temperature to the lower temperature. So heat energy will flow from the surface of the sun to the surface of the red giant star. Then I mentioned that when this happens, the red giant star expands while sun contracts. Now, who tells me this? Why is it that when heat energy flows into another star, excess heat energy will make the star expand? Can we actually get it from some physical expression? All right. And indeed, one can, but for that, I have to use virial theorem. I will, as I told you, that I will not prove virial theorem in the class. Normally, whenever we teach classical mechanics in our first semester MSc, virial theorem is proved. I will assume that virial theorem has been proved. Those students who are not from the Department of Physics and Astrophysics, they can just assume that the virial theorem is correct. Okay. So just take it for granted that the virial theorem is correct. Now I will go very slowly and prove certain result. I'll go very slowly. They are all very simple. So students who are from other departments other than physics and astrophysics, remember, it's very simple. It is just that because you are not familiar with the terms, you might initially feel that these are difficult, but let me assure you, it's only a matter of familiarity. Once you become familiar, you'll find it's all very simple. And sometime or other, the principles that I discuss will also be useful in your own research work because these are part of thermodynamics or simple quantum mechanical results like energy is equal to h into nu and so on. So just bear with me for a while. These are very simple ideas. All you have to do is become more familiar by, as I said, that these are all described in a simple manner in Frank Schu's book entitled The Physical Universe. Do some simple numericals so that you become familiar with it. It's only a matter of becoming familiar. All these concepts are very simple. So let me go to that uh, let me go to that derivation part. Okay. Okay. I hope you are able to see the slide. I see that there is a question. Yeah, so Priyamvada has asked a question. Yes, Priyamvada, you're right that although Betelgeuse is uh, showing a lot of variability, we cannot be sure whether it is going to turn into a supernova in another 20, 30 years or 10,000 years. We cannot be sure. But again, uh, we can be hopeful that within our lifetime, perhaps Betelgeuse would uh, explode into a supernova. And the hope is for the reason that when we have a supernova going off in our neighborhood, lot of interesting physics studies can be done. For example, theoretical ideas concerning supernova collapse tells us that the core, when it collapses either to a neutron star or if the core mass is very large to a black hole, neutrinos are emitted and many pulsars or the neutron stars, they are shown to be having very large velocities, and it is believed that when the core collapses there is a prenatal kick given to the neutron star or the black hole, and no one understands why, what gives rise to this prenatal kick to the compact remnant that is left behind after a supernova explosion. And furthermore, gravitational waves. One knows that whenever there is an explosion which has deviation from spherical symmetry, then there'll be emission of gravitational waves. And since LIGO is operational, if Betelgeuse indeed turns into a supernova, LIGO will detect the gravitational waves for the first time from supernova. So far, LIGO has only seen gravitational waves from binary compact objects. But if Betelgeuse turns into a supernova, LIGO will certainly see a strong gravitational wave amplitude. Uh, so, therefore, uh, astronomers are studying keenly Betelgeuse. Hopefully, within our lifetime or within your lifetime, Betelgeuse explodes into a supernova. Right. So, I hope you can all see the slide where I will discuss virial theorem and slowly go over to the a very simple idea describing the white dwarf stars. All right. Okay. So let me first, I will, as I said, I will only give the statement of the virial theorem. But before I talk about virial theorem, for those who uh, have stopped studying after school, their memory has to be freshened up. All right. So we know that if an object has mass m and if it is moving with speed v, then it has a kinetic energy. And the kinetic energy is given by half mv square. In other words, if I take an example, let's take a cricket ball and assume, I will assume the values for the sake of churning out numbers faster. So if you assume that the cricket ball has a mass 100 gram, and let's say I throw the cricket ball with a speed, okay? Again, I am assuming a number so that quantities are mentally one can compute. So suppose I throw the cricket ball very fast with a speed of 10 meters per second. Okay. So again, let me remind you, mass of the cricket ball I have taken to be 100 grams. Speed I have taken it to be 10 meters per second, which is nothing but 1000 centimeter per second. And I ask, what is the kinetic energy of such a cricket ball? So 1000 centimeter per second, when you square it, you'll get 1 million centimeter square per second square. 1 million centimeter square per second square. Mass is 100 gram, but 100 divided by 2 is 50. So 50 times 1 million, or in other words, 5 followed by 70 erg of energy such a cricket ball will have. So 10 meter per second translates to 1000 centimeter per second. Square makes it 1 million centimeter square per second square. Mass of 100 gram divided by 2, 50 into 10 raised to the power 6, which is 5 into 10 raised to the power 7 ergs of kinetic energy. And as an exercise, so please take it as an exercise. Remember, apart from the assignment set, time to time, I have given you questions orally, and please do them, because similar questions can come in the exam. So whatever questions I give orally during my lecture, you must do it so that you get an idea, quantitative idea about various things that I have been teaching. So do the following exercise. Our Earth is going around the sun with a speed of about 22 kilometers per second. For the sake of rounding of numbers, you might take it to be 20 kilometers per second. I want you to calculate the kinetic energy of Earth. Of course, kinetic energy depends upon the frame of reference. I mean, you're measuring speed with respect to a frame of reference. So I want you to estimate kinetic energy of Earth with respect to the barycenter, meaning roughly with respect to the sun. Barycenter is the center of mass of the full solar system, but take it as a very simple thing, that calculate the kinetic energy of Earth with respect to the sun, given the fact that Earth's speed is about 20 kilometers per second. But remember, whenever you are doing the calculation, you have to convert everything either to MKS unit or to CGS units. So don't make the mistake of combining things, one evaluated in MKS, other evaluated in CGS, then you will get a nonsensical result. Okay, so please calculate the kinetic energy of Earth with respect to, in the frame in which sun is, let's say, static. The other kind of energy which is very important in all aspect of science is potential energy. So we all know that you could have potential barriers in chemical reactions. So when you do chemical kinetics, you very often talk about activation energy to climb across the potential barrier. So potential energy is a very important quantity, and it is an energy associated with forces in your problem. unlike the kinetic energy. Kinetic energy doesn't depend upon the forces acting on a particle. Kinetic energy only depends upon the kinematical variables like mass, velocity, and so on. So, if you take gravitational, so here I am concentrating on gravitational potential energy. So, if you take a gravitational potential phi, if the particle is moving in a gravitational potential phi, then the gravitational potential energy of the particle will be m times the gravitational potential. So remember, this is potential and this is potential energy. As an example, we have already talked about when we were describing escape velocity. If you take a point mass or a spherically symmetric mass capital M, then for a symmetrically distributed mass, total mass being capital M, if you go outside that distributed mass, then at a distance d, the gravitational potential is minus g capital M divided by d, where capital M is the mass of the gravitating object. So that a particle of mass small m would have gravitational potential energy m times 5 or minus g capital M multiplied by small m divided by d if it is at a distance d. Right. Therefore, the total energy of the system of this particle will be its kinetic energy plus its potential energy. Okay. Now, I will state the virial theorem. Don't bother about the proof. I'll just state the virial theorem. Suppose you have a collection, a system of many particles, and they are moving with different speeds, and they are in a gravitational potential V phi, and therefore, because there are many particles, they are all moving with different speeds, there'll be a potential energy for every particle, and hence the total kinetic energy will be sum of the kinetic energies of the type half m1 v1 square plus half m2 v2 square, etc. Similarly, gravitational potential will be m1 into phi at the position of m1 plus m2 into phi at the position of m2 and so on. And one can, for the entire system, write down the total energy to be total kinetic energy plus total potential energy. But of course, if you have a large system, you cannot keep track of individual particles. So you can ask, what is the average kinetic energy? What is the average potential energy? Because a huge blob of gas or a huge blob of birds flying, as you know, if you view a large collection of birds flying, then the birds, their shape as they fly about, they change and all that. Virial theorem states that if you have a large number of particles having kinetic energy and gravitational potential energy, actually the theorem is about any bound potential, need not be gravitational. But here I have only given you an example of gravitational potential energy. But this theorem is valid for every potential, every attractive potential. The virial theorem states that when a system is bound meaning what? That it cannot by itself spread all of them into infinity. That means for a bound system, the total energy must be negative, because if they spread to infinity, then potential at infinity will be zero, and if there's just spread, that means total energy is either zero or positive. So in order that a system remains bound, that means they over time they don't become infinitely large size, the total energy has to be negative. So a bound system, that means total energy is negative, and it is in equilibrium so that its shape is not changing appreciably. For such a condition of a bound system whose shape is not changing, the Virial theorem states that twice average kinetic energy must be equal to negative of average potential energy. Average meaning what? Everyone knows some amount of statistics. Average meaning, suppose I have masses m1, m2 up to mn, moving with speed v1, v2 up to vn, then average kinetic energy will be half m1 v1 square plus half m2 v2 square up to half mn vn square. Add them all up and divided by n. Then that will be the average kinetic energy. Similarly, average potential energy you can also calculate. What Virian theorem asserts is that twice average kinetic energy must be negative of average potential energy. Let me pause for a little while and make some remarks. Note that kinetic energy is always positive. Why? Because v square is a square of a number, it is always positive. Mass of a particle, so far all the particles we have detected in nature, their masses have been shown to be positive. We have never found any particle with negative inertial mass. So kinetic energy is always positive. So virial theorem works only when you have an attractive potential, so that potential V becomes more and more negative as you come closer. When you put systems close to each other, the potential energy must become more and more negative. And as the system, constituent members of the system go to infinity, the potential energy goes to zero. And therefore, the average potential energy is always negative, so that minus average potential energy is always positive. And that's the reason why there is no contradiction in the theorem that a positive number on the left hand side, indeed, the right hand side number is also positive, because potential energy is negative for an attractive system. And because the system is bound, the average total energy, which is sum of average kinetic energy and average potential energy, is also negative, in order that the system is bound. So, to summarize, what we have established so far is that if you are talking about a bound system, a system made out of many particles moving in a potential that is attractive, and let's say the shape of the system is not changing, those who are physics student, by shape I mean the moment of inertia. The Whenever the second derivative of moment of inertia is zero, then you get this result of virial theorem. So if you have a bound system whose shape is not changing appreciably on an average, then the theorem says twice average kinetic energy is negative of average potential energy, and bound system means average total energy is less than zero. Okay. Now, let's come to thermodynamical system, because we are talking about stars, and stars are hot gaseous system. When you have a hot gaseous system, meaning thereby either atoms or ions like electrons and protons, they are hot and randomly moving, the kinetic energy will be the random kinetic energy of the electrons and the protons. But now we are talking about a gaseous system like a star. And therefore, you would wonder that even 1 gram of hydrogen, if you take a jar of hydrogen gas, and let's say the total mass of the hydrogen, atomic hydrogen gas is only 1 gram, then I know that number of hydrogen atoms in this 1 gram of atomic hydrogen is around 6 into 10 to the power 23. There's the Avogadro number. And we know that gram molecular weight of any element has the same number, namely Avogadro number of that element's atoms. By the way, um, those who are mystified where it comes from, this is not generally discussed in the book, but it is just the fact that it's a statement of the fact that proton's mass, okay, is 9 into 10 to the power about 9 into 10 to the power minus 24 gram. It's just that fact. And the fact that neutron's mass is almost equal to proton's mass, and the atoms, the binding energy, electromagnetic binding energy is negligible. So that the total mass of the atom is basically the mass of the neutron plus protons. So those who take it as a want to do it as a puzzle, please show that the Avogadro hypothesis that gram weight of any element, gram atomic weight of any element has Avogadro number of that element's atoms is just related to the fact that proton's mass is about 9 into 10 to the power minus 24 grams. I have digressed a bit. Let me come back to astronomy. Right. So, for a gaseous system which is in thermodynamic equilibrium, let's say the gaseous system has a temperature temp. I'm calling the temperature temp because I've already called kinetic energy as T. So therefore, I don't want you to be confused by using the same T for the temperature. So in this slide, T is the kinetic energy, while temperature of a gaseous system, I'm calling it temp. Okay. And if I have a system of gas at a temperature temp, then I know that for every degree of freedom of the particle constituting the gas, either electron or protons, for every degree of freedom of a particle, the associated thermal energy is half kb times its temperature. Kb is the Boltzmann constant. And Boltzmann constant, of course, is very important, not just for physics, but also for chemistry and biology, because uh, living systems, their metabolic rates go up as the thermal energy kbt for every constituent goes up. So this, I'm sure, is familiar with students from chemistry, students from biology, etc. So every degree of freedom of a particle, which is in a system at a thermal temperature temp, every degree of freedom will have energy half kb times temperature. This is normally proved in statistical mechanics course under the uh, term equipartition theorem. Okay. Therefore, if I take a system of electrons and protons, then electrons and protons, if they are just gaseous particle moving in three dimension, they have 3 degrees of freedom. I am omitting their spin degrees of freedom. Okay. And then if the total number of electrons plus protons is n, therefore the kinetic energy will be 3 by 2, because 3 times the degree of the half kb temperature, with the 3 degrees of freedom. Then the total kinetic energy, after all, thermal energy is nothing but random kinetic energy. So the average, so total, these are not, I'm not talking about the average, but total average kinetic energy. This average is not the statistical average where I average and sum it up divided by n. By average, I mean time average. So the time averaged kinetic energy, random kinetic energy, which is same as thermal energy, time averaged thermal energy or time averaged random kinetic energy of a system of gas having a total number of electrons plus protons to be n is given by this number by virtue of equipartition theorem. And what is the total number of particles? If the total mass is m for the system, then m divided by the proton mass, electron's mass is negligible compared to the proton mass. So total mass divided by proton mass will give you the number of particles. Hence, the average kinetic energy is simply given by 3 by 2, total mass of the star divided by proton mass, Boltzmann constant times temperature. While what is the total time averaged potential, gravitational potential energy? As I earlier said, that if gravitational potential is minus G capital M by R, and if you have a test particle with small m mass, then the total gravitational potential energy is minus G capital M small m by R. But here I'm talking about the entire gravitational potential energy of the star. So I have to sum up over all small m. So effectively, my time averaged gravitational potential energy of the entire star is minus gm square by r, where m is the mass of the star, r is the radius of the star. By virtue of virial theorem, what is virial theorem? Equation 4, that twice time averaged kinetic energy is minus time averaged potential energy. So twice this factor of 2 will go, and I have 3 times mass of the star by proton mass, Boltzmann constant times temperature of the star, minus of minus time average potential energy, minus will become plus gm square by r. One factor of mass will cancel with m square, so that you have only one factor of mass of the star, and we get the result that the temperature of the star is simply Newtonian gravitational constant times total mass of the star times proton mass divided by C times Boltzmann constant times the radius of the star. Here, let us take a pause at equation 8. It tells us that bigger the star is when it is in virial equilibrium. If R is small, temperature is small. While if R is big, temperature is small. And if R is small, temperature is large for the same mass M. Remember the examples of the red giant and the white dwarf I talked about. I said red giant, when sun becomes a red giant, the radius becomes very large, and I said it becomes redder. Why does it become redder? Because of this result that temperature is going down with the size of the star, and since a sun-like star, when it becomes very large, temperature has to come down, and hence from Jean's law of blackbody radiation, the color, the wavelength will become longer, and that's the reason why the surface of the red giant star appears red. On the other hand, if you take sun and if it just becomes a white dwarf, that means R becomes very small, the surface temperature becomes very high. So R becomes small, temperature becomes very high. That's the reason why Sirius B, although it is very faint because its radius is smaller, but the surface temperature is very high for Sirius B. Okay. What about total energy? We can also calculate the total energy coming out of this result. Total energy, time average total energy, is a time average total kinetic energy plus time average total potential energy. But by virtue of virial theorem, we know that time average kinetic energy is minus half time average potential energy. Remember the virial theorem? Virial theorem tells me, equation 4, virial theorem tells me that twice time average kinetic energy is negative of time average potential energy, and hence the total time average total energy of the star is time average kinetic energy plus time average potential energy. But by virtue of virial theorem, time average kinetic energy is minus half time average potential energy plus potential energy. So therefore, half of time averaged potential energy. Potential energy is minus gm square by r, and therefore total energy is simply minus of the order of minus gm square by 2r. Not a surprise that it is negative, after all it's a bound system. So total energy indeed is negative. Now look at these two results. Total energy is negative, of course, because the bound system. Star's total energy is negative. And for a given mass m, the total energy, because the size of the star is in the denominator, if r increases, then the total energy actually increases because it becomes less negative. If r becomes larger, gm square by 2r becomes smaller, but there's a negative sign. So minus 2 is bigger than minus 4. Minus 4 is bigger than minus 10. And hence, if r becomes bigger for the same mass, the total energy therefore becomes larger. While if r shrinks, the total energy becomes more negative. That means it decreases. In other words, this equation tells me for a given mass m, corresponding red giant has more total energy compared to a white dwarf of the same mass. That is the reason why in our thought experiment, when I connected sun to a red giant and heat flowed from sun to the red giant, its radius increased. Why? Because when the heat flowed, the red giant star got more energy. But if it gets more energy, by virtue of this equation, if it gets more energy, R must increase. So the radius increased. By virtue of Fourier theorem, if radius increases, temperature goes down. And now you see why in the thought experiment, when I connect sun to a red giant and thereby heat flows from sun to the red giant expands and thereby the temperature goes down while sun shrinks. Why does it shrink? It has lost energy, so its total energy becomes even lesser, so R must therefore decrease. But if R decreases, a shrinking sun's temperature will go up. The sun becomes hotter and hotter, red giant becomes cooler and cooler, and you have a thermodynamic runaway situation. What I will do is I will stop here and take questions. Okay? I'll stop here and take questions. All right. So let's see what are the questions. Yeah, Shubham is asking, is there fluctuation noticed in sun's radius? Yes, it is noticed because solar observatories, when they look at the sun closely, they see that the surface of the sun exhibits solar oscillation modes. There is the radius at very small scales compared to sun's radius. It is there is oscillation. There is a 5 minutes oscillation and so on. And that is the reason why I have been using the term that stars are not in full hydrostatic equilibrium, but they are in quasi hydrostatic equilibrium. Okay. There is no nuclear explosion that is taking place inside the sun. Explosion means what? When you say that there is an explosion, what one means is energy released in a very short time scale. That means whenever energy is released suddenly, that is what is an explosion. While the thermonuclear reaction that is happening inside the sun is a controlled thermonuclear reaction. And the time scale over which changes are happening in the core of the sun is larger than 10 to the power 8 years. Unlike a supernova explosion, in a supernova explosion, in few millisecond time, the entire energy is released to the envelope of the star and the envelope explodes. That's why it's an explosion, because in millisecond time scale, energy is deposited onto the envelope of the star, while in the case of sun, time scale of the thermonuclear process is more than 10 to the power 8 years. That means the changes that happen in the core, they will take more than 10 to the power 8 years. So therefore, a sun-like system is in a quasi-hydrostatic equilibrium, where in the core you have a controlled thermonuclear fusion going on. As you know, in our plasma physicists and nuclear physicists, they are struggling to have controlled fusion in the laboratory. There's a whole project called ITER. It's an international project where they are trying to obtain controlled thermonuclear fusion in tokamaks. But tokamaks so far can only have controlled nuclear fusion for few minutes. Unlike the sun, in the case of sun, the controlled nuclear fusion is going on for more than billion years. And you might ask, why is it happening in sun? It is because of the gravity. The entire gravity of the whole shell of matter around the core stops the thermonuclear reaction in the core to become explosive. Okay. Okay. Now, regarding the other question of Shubham, uh, the new hydrostatic a new hydrostatic equilibrium will happen only when the sun becomes, say, red giant. At the moment, it is doing fine as a main sequence star in a quasi hydrostatic state. Yes, now I come to Priyamvada's question. You're right that if you have a system in which there is repulsive gravity, then the gravitational potential energy will be positive. And that can be seen that the gravitational potential energy of mass capital M is minus G capital M by R. If M becomes negative, if you discover a system for which mass is negative, M becomes negative, so minus Gm by R will become positive. So therefore, you will have now a positive potential energy for a repulsive gravitational potential. Yes, Glena, uh, I will send you the PDF of this file in the evening. I will also send you, I mean, everyone, I will send you my second assignment set soon. And I will also send you the PDF of this file either today or tomorrow, because there are still some portions that I have to fill it up carefully. And I will send the PDF. I will do that. There is another question by Priyamvada. She is asking whether we can observe Ratna. There is something which has come. Priyamvada is asking that if something is moving in a completely homogeneous and isotropic environment, okay, and there is no other observer, if there is a single observer and the single observer is moving in a matrix of gas which is homogeneous and isotropic, and if he is moving uniformly, can he determine its velocity? The answer is no. That's part of the special relativity. In special relativity, velocity is uniform, and therefore, velocity is determined with respect to another frame of reference. So if you have a single observer moving with respect to a homogeneous and isotropic continuum, if it's a continuum which is homogeneous and isotropic, you can't make out even the relative velocity of yours with respect to points on the continuum, because there's no point in the continuum. If it is homogeneous and isotropic, every point on the continuum would look the same, and therefore one will not be able to measure one's speed with respect to the continuum. For a completely homogeneous and isotropic system. But of course, we don't have such homogeneous and isotropic objects which are continuum. Why? Because already we know from Einstein's analysis of uh, Brownian motion that gas or fluid are not, they don't form a continuum. They are all made up of discrete particles like atoms and molecules. So even if the gross density and the pressure of the gaseous matter through which you are moving may appear homogeneous and isotropic, but they are atoms and molecules. So if you have a fine microscope and a telescope, you'll be able to figure out that you're moving with respect to this atom and with respect to that atom, and thereby you can measure your relative velocity. So, in other words, to answer your question, Priyamvada, that in the real world there is no continuum medium which is absolutely homogeneous and isotropic, and therefore, even one is moving uniformly, one can measure one's velocity with respect to these discrete atoms and molecules that make up the medium. Of course, if you are not moving uniformly, then you will experience a fictitious force, the so called pseudo forces. Then, of course, you know that you are accelerating. So, therefore, to answer your question, it is not just a matter of perception. Ultimately, in physics, we do accurate measurement to find out the state of a system or the state of our motion. So, it is all part of accurate measurement. It's not just some emotional feeling or a human feeling or human perception. Science is beyond all these. So, therefore, indeed, relative motion can be measured when you take into account sensitive measurements. Okay. Uh, Coming to the next question, Khushi Arora's question. That's a very good question. So her question is, can you apply virial theorem to black hole? The answer is no, because the black hole by itself is a space-time singularity, which is a solution of general relativity, while virial theorem is established for non-singular systems, which are macroscopic. So, an isolated black hole, you can't apply virial theorem, standard virial theorem to an isolated black hole. What you can do, however, is that if gaseous matter is present outside the event horizon of a black hole, and let's say due to high thermal energy of the gaseous matter around the black hole, for a long time, this gaseous matter is in a quasi hydrostatic equilibrium around the black hole, then you can apply the virial theorem for this gaseous, hot gaseous matter around the black hole, taking into account the gravitational potential energy also arising due to the black hole. Okay. Next question is by Ankit. And Ankit is asking, universe is expanding. Well, strictly speaking, you can't use twice average kinetic energy equal to minus potential energy for the universe. The universe is expanding. The shape is changing. So therefore, you cannot talk about the application of twice average kinetic energy equal to minus average potential energy as a approximation of expanding universe. The fact is universe expanding. And furthermore, for the whole universe, you cannot use the Newtonian dynamics for the simple reason that the universe, total mass of the universe is huge, the length scales are huge, so the gravitational potential energy is very large. Strictly speaking, one must use general theory of relativity to understand the details of the expanding universe. But yeah, you can, in a local neighborhood, you can use Newtonian gravity plus expansion to get some interesting results which are approximately correct. But real universe, you have to use general relativity. In fact, as you know, even before Hubble established the expanding universe through observation, there was Friedman solution where the Friedman assumed uniform density and isotropic density of matter, and he got exact solution where you have either an expanding universe or a contracting universe. And few years later, uh, a bishop called Lemaitre, George Lemaitre, Belgian bishop, he independently rediscovered Friedman's solution, but he published it in a obscure Belgian journal. And in fact, he later on also published a paper where he said that universe is not static, but the universe is expanding. Much before Hubble actually discovered the expanding universe. But unfortunately, his paper, being in Belgian language, no one had taken notice of George Lemaitre's work. And that is the reason why today we call the expanding model of the universe as Friedman, Lemaitre, Robertson, Walker model. So you need general relativity to describe the expanding universe. Shubham is asking, well, giant means size has become very large. And as I described qualitatively, the reason why uh, after the core has turned into helium and then helium burns to form other elements like carbon, oxygen, nitrogen, what happens is that the core, once if you take a sun-like star and the core is now totally composed of carbon, oxygen, and nitrogen, and they are in plasma form, right? No further nuclear fusion can take place. Why? Because for a sun-like star, again you can use the virial theorem. Virial theorem, the expressions I have written down, as you can see in the virial theorem, that temperature, here you can see the temperature. Temperature is directly proportional to mass and inversely proportional to R. So if the mass of the star becomes larger, the temperature can be larger. But for the sun-like star, the core temperature cannot become so high as to start the fusion of carbon and carbon or oxygen and oxygen, because they are heavier elements with nuclear charge being very large. And when the nuclear charge is very large, the electrostatic repulsion between a carbon nucleus and the oxygen nucleus is huge. Therefore, one needs much higher temperature to overcome the electrostatic equilibrium electrostatic repulsion between a carbon nucleus and the oxygen nucleus so that there is a fusion. So low mass stars like sun, you cannot burn heavier elements like carbon and nitrogen. And therefore, once the core becomes carbon, oxygen, nitrogen rich for a star like sun, the core nuclear fusion stops. What will happen? As the core nuclear fusion stops, no more energy production. So the core starts cooling. If the core starts cooling, again the virial theorem, if the temperature goes down, R, your temperature is going down and the heat content is also going down. So R must shrink. So once the radius shrinks, the envelope outside the core, that also shrinks. But if the envelope, what is the envelope outside the core? That is still made of hydrogen. The envelope outside the core, if it further shrinks, that means R decreases, the temperature goes up. And then the envelope, if the temperature goes up, again proton fusion can start. So the protons will start undergoing thermonuclear fusion in the envelope and energy will be released. So the envelope temperature goes up, but envelope, it is at a higher radius compared to the core. So the gravitational force that the envelope experiences is lower, inverse square law of gravitation. And therefore, if suddenly the envelope becomes hot, the envelope can expand very easily. And it is this expansion which makes the envelope expand further. And that's how the sun becomes a red giant. Giant meaning the radiance becomes so large. Today, sun's radius is 6.96 into 10 to the 10 centimeter. But when it becomes a red giant, 1,000 times its radius will become 1,000 times bigger and it will engulf Earth when it becomes a red giant. And that is the reason why it becomes a giant. Well, as I said, for a red giant, in the beginning, when it expands, yes, the temperature goes down, but the core is still very hot. So for a while, there'll be a quasi hydrostatic equilibrium. But just like I was talking about Betelgeuse, which is a giant, eventually, when it cools down, it can't support against gravity and it will collapse. The core will collapse and it will undergo a supernova explosion. Precisely what you're stating is that yes, the temperature, surface temperature for the red giant has gone down, but the core remnant heat is still there. The core is still very hot. And once the core temperature goes down so that there is not enough pressure to halt the gravitational collapse, once the pressure goes down, it will collapse. And that's what we expect of Betelgeuse. And once it collapses, there's no more hydrostatic equilibrium. Shubham is asking, why can we use Kepler's law for black holes? Not when you are very close to the event horizon, but if you are very far from the event horizon, then Newton's gravity is an approximate gravity and it follows from Einstein's general theory of relativity. So what do you compare? When do we say that Newton's gravity can be used? If you find out that the gravitational potential, its magnitude is much less compared to square of the speed of light, then one can use Newtonian gravity without making much error. So very far from a black hole, you can use Newtonian gravity. After all, the Milky Way black hole, our center of our galaxy as a supermassive black hole, 4.5 billion solar mass black hole. But we don't have to use general relativity for the motion of our solar system going around the center of our Milky Way, because we are so far that the gravitational potential due to the black hole at 8 kiloparsec, where we are, is much, much small compared to the square of the speed of light. So Newtonian theory is sufficient. Only when you go very close to the event horizon, then Newtonian theory cannot be used. They will be no longer valid, because potential magnitude of the general relativistic gravitational potential energy would be comparable to the square of the speed of light, and one necessarily have to use the general relativity. So when in my last talk I was talking about v square equal to gm by r, that was assuming that the stars were far away from the event horizon of the Milky Way black hole. Once you go close to it, you have to do full general relativistic calculation. As you know, uh, Professor Andrea Ghez and independently Professor Reinhard Genzel, they have also monitored the motion of the star S2, which is going around the supermassive black hole. And S2's orbit is not Keplerian orbit at all. In fact, the the closest point to the black hole, it precesses. So the orbit is not a fixed ellipse, is actually a precessing ellipse, and that follows from general relativity. Okay, there's another question by Hrishika. Yeah, so as I mentioned as an answer to Shubham's question, so when you have a red giant star, the red giant's lifetime will be very large. It will be of the order of 10 to the power 6, 10 to the power 7 years. It all depends upon the rate at which the core is cooling down. Ultimately, one of the questions that was given in the assignment set 1 is what causes the quasi hydrostatic equilibrium? It is the pressure gradient. So how high is the pressure of the core? Can it support the entire weight of the envelope surrounding the core against its own weight? So as long as the core is still very hot, the remnant heat, because once the nuclear fusion stops, no new energy is being generated, and therefore one has to find out what is the time scale over which the remnant heat of the core decreases, so that the core is no longer able to support itself against its gravitational collapse. That means the core mass for a while degenerate pressure will support it, but eventually it will collapse. So once the core mass is more than 1.4 times sun's mass, then as the white dwarf core cools down and its mass is more than 1.4, so no more white dwarf equilibrium state, I'll just collapse. And the collapse happens at a very fast time scale. We will see how this time scale is estimated later on. That also we will discuss. But a core will collapse within time scale of few milliseconds once it becomes cold. But From what we see of Betelgeuse, the core is still hot, and therefore Betelgeuse has not yet turned into a supernova. Okay, right. Are there any more questions? Again, as I have mentioned, that don't hesitate to ask any question. But I tell my students that no question is meaningless or superfluous. All questions are very important. So don't hesitate at all to ask any question, because science progresses only when you disbelieve someone. So don't believe anything that I say. You must ask question, and I must be able to give you logical answer to support my argument. Science progresses only when you don't believe what is already said. If you believe whatever has happened in science, then the science will never progress. So please feel free to ask questions. As you know, Penrose's work in 1965, where he proved singularity theorem, he proved it to show that the earlier work by some Russian scientists like Khalatnikov and others, they have showed that you can't have singularities. But Penrose realized that there might be a mistake in the analysis, so he did a calculation. If you took the attitude, oh, Khalatnikov et al. Have already shown that there is no singularity and we should not ask question, then uh, you wouldn't have proved the singularity theorems. The science progresses only when you don't believe and pursue your own analysis, but with great physical insight and accuracy. That's the reason why quantitative thinking in science is very important. Just uh, making picture like thinking is not enough. Picture like thinking can influence you to get excited about an idea, but eventually whether your idea works or whether your idea stands to the scrutiny of laws of physics or laws of science, you have to do more accurate logical and quantitative estimate. So that is the reason why in this course I am slowly uh, making things more quantitative, because in science you have to be quantitative, whether it is physics, chemistry, or biology. In biology also a lot of measurement is done. Any measurement will bring you quantitative aspects anyway. Right, so there is a question by Kushi. Well, I don't know whether indeed what you are saying is correct, why iron is more abundant than nickel. I don't know whether it's true globally in the universe. It may be so on the crust of the earth, but how do you know that the average iron density everywhere is more than the average nickel density all over the Milky Way galaxy? So I'm not sure that your statement is true. I have to figure it out. But let me ask you, Kushi, why do you say that iron is more abundant in the universe than nickel? Who gave you this number? Because as far as I know, that our knowledge of abundance in the universe is well known for hydrogen, for helium, for light elements like lithium, deuterium. Even for deuterium, there is a great deal of uncertainty, because even the creation of deuterium in the Big Bang nucleosynthesis, there is also sputtering or spallation. They can be broken up by high energy radiation. So, can you tell me, Kushi, why or who told you that iron is more abundant all over the universe compared to nickel? And I don't think we have sufficient measurement to claim that iron is more abundant than nickel. Well, Kushi, you can think about it and you later on can give me the source from which you have found out that iron is more abundant than nickel. So please let me know later on. But at the same time, one must also mention that iron plays a very important role. In fact, neutron star, the reason why neutron stars form is that once you have a very massive star, as you know, for a very massive star, the nuclear thermonuclear fusion can take place in core where carbon, nitrogen, oxygen, they can undergo thermonuclear fusion, and because the mass is so high that temperature can go up, and thereby the thermonuclear fusion will proceed. Once it forms iron, then of course no more thermonuclear fusion can take place. Why? But as Kushi is mentioning, that binding energy per nucleon for iron is the largest. That means iron nucleus is the most stable nucleus. Therefore, you cannot take one iron nucleus and take another nucleus without supplying extra energy. You cannot make an iron nuclear fuse with another nucleus. You need more energy because by itself it will not happen. The iron is already the most stable nucleus. Of course, if you supply more energy, then it can undergo thermonuclear fusion, and that's the reason why on Earth we do have uranium, which is whose atomic number is 292 or 293. So you might ask, where did the uranium nucleus got synthesized? It's because of supernova explosion, where the blast wave, it already had so much of energy, it gave energy to also synthesize heavier elements. Kushi, no, I won't trust Wikipedia. I would need some research paper which says that iron is more abundant than nickel. I would require some research papers. What might be mentioned is the detection. I mean, because iron can be also detected in X-ray line. Like there's a 6.4 or 8.4 kiloelectron volt X-ray line, which is a signature of the iron, and one can, through X-ray telescope, one can therefore measure the iron easily by studying this 8.4 keV line. And if nickel doesn't have such characteristic line, we can't detect it. But that is because of our experimental or observational limitation. So I would need to look at a research paper to see indeed what you are saying is correct. Shubham is asking another question. Well, for the n equal to one state, yes, n equal to one state has the wave function which doesn't go to zero at r equal to zero, the so-called S state. The S state of the wave function is proportional to e raised power minus r by 2a, where a is the Bohr radius. So e raised to power minus r by 2a is actually increasing as r goes towards the nucleus. But it is the total wave function. It is a violation of uncertainty principle will happen if you say that uncertainty in the position for this wave function is of the order of the nuclear size of one Fermi. That is not true. If you take e raised to power minus r by 2a, then the probability density of finding the electron will be proportional to e raised to power minus r by a. That means that itself is telling you that uh, when you calculate the probability, that means the average value of r. How do you find out the average value of r? You take the expectation value of r given the probability density, and you will find that the expectation value of r is the Bohr radius itself. And that means, on an average, the electron in a hydrogen atom is lying at a position, on an average, of Bohr radius. And similarly, if you calculate the uncertainty is much, much, much larger than the size of the nucleus. And therefore, there is no problem. Only if you try to say that the electron is confined within one Fermi, there is a problem. Why? Because within one Fermi, if you try to localize the electron, the uncertainty in the momentum will be so large that the corresponding energy will be so huge that it will not be able to keep the electron by electrostatic force to the nuclear region. And that's a standard thing we do in modern physics exercise to prove that electron cannot lie within the nucleus, because the uncertainty in the energy will be so large, the electrostatic attraction between the electron and the proton will not be able to keep it to itself. You can use actually the virial theorem for doing this calculation. So as I'm telling you everyone, uh, don't stop at only thinking in a pictorial manner. Go slightly more to the quantitative aspect. So sit down. Yes, pictorial thing. It's a good thing that you're using your picture and intuition. But as I said, that is not sufficient. Develop the habit of taking a pen and a paper, and whatever pictorial imagination has given you an idea, try to work out the idea in terms of numbers using standard principles of physics and do some calculation. And you will find that the calculation will tell you much more than the pictorial thinking. All right. So, for example, I mean, just to, because now there are only 7 more minutes left, and I don't want to embark into a simple way of looking at the white dwarf star now, because it involves many new concepts which might be unfamiliar to students who are not of physics and astrophysics department. So let me therefore, in the remaining time, give you certain small ideas so that you can think of, you can use your imagination and intuition. So one of the things you can think of is, can we use the kinetic energy of celestial objects to power um, uh, various uh, engine on Earth? For instance, because we know that there is a energy crunch energy resource crunch which we are facing, because once the petroleum products, as you know, so far the greatest energy resource that is being used is the petroleum product, the so-called hydrocarbon based energy resource. But except USA, most countries will soon um, exhaust all their energy resource. USA has untapped petroleum resource in the Alaska region, and they are going to have the petroleum resource for a very, very long time. But rest of the countries will soon exhaust their petroleum resource. The question is, can we think of having alternate source energy resources? So people are already working solar energy, the tidal energy, wind energy. Many ideas are there. So you might think that, well, moon itself is going around Earth, and moon has therefore a lot of kinetic energy. So first estimate the kinetic energy of moon with respect to Earth, and think of ways can we draw out the kinetic energy of the moon. That means slow down the moon. And we may not worry about if you slow down the moon, then you might think that moon will slowly spiral and come closer to the Earth and eventually fall into the Earth. As I told you some time back, the tidal torquing is actually making the moon go away. So therefore, if you slowly, slow rate, you can draw the kinetic energy of the moon, uh, then you might stop moon going away from Earth. But before you think whether this idea is um, feasible or it's just a crazy idea, I ask all of you to do the simple exercise. Find the kinetic energy of the moon currently and think of ways how would you able to extract the kinetic energy of the moon. So please think about it. The other question I have is, do you, can we, instead of today, can we schedule uh, a lecture tomorrow at 10:30 instead of having the afternoon lecture today? Because I'm sure that if I start my afternoon lecture at 4 or 4:30 on new topics concerning white dwarf, uh, most of you will not be able to absorb it, because brain after all has a limited capacity to learn new aspect. So therefore I am asking, can we schedule the talk where I will introduce Heisenberg uncertainty principle and how to make use of that to understand the basic idea regarding white dwarfs. So these will be new ideas, particularly for students who are not of physics and astrophysics department. And therefore, I would like the next class to be scheduled tomorrow, either in the morning or afternoon. It is up to you. So, can we do that? So, is it all right if the next lecture is held tomorrow at 10:30 instead of today afternoon? I know that tomorrow afternoon you might be interested in seeing the uh, Ravan effigy being burnt, and through, I mean, through video, not that you should go out in the crowd to watch it. So you might be interested in the afternoon. So maybe 10:30 in the morning tomorrow, we can hold the next class. Is it all right? Very good. I think many of you have already said tomorrow. So our next class will be tomorrow at 10:30, Sunday at 10:30. Great. So, um, so have a great Dashera, all of you, and we will meet tomorrow at 10:30 a.m. And but be safe, take care, don't go out into the crowd, but enjoy otherwise. Goodbye for now.